The superplane was a marvel of modern engineering. It represented the pinnacle of human achievement in aviation, a testament to the relentless pursuit of excellence and innovation. This aircraft was not just a mode of transportation. It was a symbol of progress, a beacon of what humanity could achieve when it set its mind to overcoming challenges and pushing the boundaries of what was possible. It was the culmination of years of research, design, and technological advancement. Teams of engineers and scientists worked tirelessly, poring over blueprints and running countless simulations. Every detail was meticulously planned and executed, from the aerodynamics of the wings to the materials used in the fuselage. The collaboration between different fields of expertise was unprecedented, bringing together the best minds in aerospace engineering, material science, and computer technology. The plane was designed to be faster, more efficient, and more luxurious than any other aircraft in the sky. It could travel at speeds that were previously thought impossible for commercial airliners, cutting down travel time significantly. Its fuel efficiency was unmatched thanks to innovative engine designs and lightweight materials. And the luxury it offered was unparalleled, with features that made long-haul flights a pleasure rather than a chore. It was a symbol of human ingenuity and our ability to push the boundaries of what's possible. The aircraft stood as a testament to what could be achieved through determination, creativity, and a willingness to take risks. It was more than just a machine, it was a work of art, a masterpiece of engineering that inspired awe and admiration. The plane was built with the strongest and lightest materials available. These materials were the result of years of research and development, offering a perfect balance between strength and weight. The use of advanced composites and alloys not only made the aircraft more durable, but also significantly reduced its overall weight, contributing to its exceptional performance and fuel efficiency. Its engines were incredibly powerful, yet remarkably fuel efficient. These engines represented a leap forward in propulsion technology, combining raw power with sophisticated engineering to deliver unmatched performance. They were designed to operate at peak efficiency, reducing fuel consumption and emissions, making the aircraft not only faster, but also more environmentally friendly. The interior was designed to provide passengers with the ultimate in comfort and luxury, with spacious cabins, lie-flat seats, and state-of-the-art entertainment systems. Every aspect of the interior was crafted with the passenger experience in mind, from the ergonomic seating to the ambient lighting. The in-flight entertainment system offered a wide range of options, ensuring that passengers could enjoy their journey in style and comfort. But for all its sophistication, the superplane was ultimately brought down by a single tiny component, a sensor. This sensor, though small, played a critical role in the aircraft's operation. It was a reminder that even the most advanced technology is not infallible and that the smallest components can have the most significant impact. This sensor, no larger than a thumb drive, played a crucial role in the plane's flight control system. It was responsible for providing essential data to the aircraft's computers, ensuring that the plane maintained the correct angle of attack and stayed on its intended flight path. The precision and reliability of this sensor were paramount to the safe operation of the aircraft. It was responsible for measuring the angle of attack, the angle between the wing and the oncoming airflow. This measurement was vital for maintaining lift and preventing stalls. The data from the sensor was continuously monitored and used to make real-time adjustments to the aircraft's control surfaces, ensuring a smooth and stable flight. The failure of this one small sensor would have catastrophic consequences, leading to the loss of the aircraft and, tragically, the lives of everyone on board. It was a stark reminder of the fragility of even the most advanced systems, and the importance of rigorous testing and quality control. The tragedy underscored the need for constant vigilance and improvement in the field of aviation safety. Modern aircraft are highly complex machines that rely on a vast network of sensors to operate safely and efficiently. These sensors are meticulously designed and strategically placed throughout the aircraft to monitor and report on a multitude of parameters. Without these sensors, pilots and onboard systems would be flying blind, unable to make the real-time adjustments necessary for safe flight. These sensors act as the eyes and ears of the plane, constantly monitoring a wide range of parameters. They gather data on everything from the external environment to the internal workings of the aircraft. This data is then processed and used to make critical decisions that affect the flight's safety and efficiency. From airspeed and altitude to engine performance and cabin pressure, these sensors cover every aspect of the aircraft's operation. Airspeed sensors, for example, measure the speed of the aircraft relative to the air around it, while altitude sensors determine the aircraft's height above sea level. Engine sensors monitor the performance and health of the engines, ensuring they are operating within safe parameters. Sensors provide crucial data to the flight control system, which uses this information to adjust the plane's control surfaces, engine thrust, and other systems to maintain stability, navigate accurately, and ensure a smooth and safe flight. The flight control system is essentially the brain of the aircraft, interpreting sensor data and making real-time adjustments to keep the aircraft on its intended path. Pilots rely heavily on the data provided by these sensors to make informed decisions about flight path, altitude, and speed. The information displayed on the cockpit screens is a direct result of the data collected by these sensors. Pilots use this data to navigate through various weather conditions, avoid obstacles, and ensure the aircraft is operating efficiently. Sensors are essential for maintaining the delicate balance of forces that keep an aircraft aloft and prevent potentially dangerous situations from arising. They help manage the aerodynamic forces acting on the aircraft, ensuring that lift, drag, and thrust are in harmony. This balance is crucial for stable flight and for the aircraft to respond predictably to pilot inputs. However, as with any complex system, the reliability of aircraft sensors is paramount. Regular maintenance and checks are conducted to ensure that all sensors are functioning correctly. Any discrepancies or malfunctions are addressed immediately to prevent any potential issues during flight. A malfunctioning sensor can have serious consequences, potentially leading to incorrect data being fed to the flight control system and resulting in a loss of control. In the event of a sensor failure, backup systems and protocols are in place to help pilots manage the situation and bring the aircraft to a safe landing. The aviation industry continuously works on improving sensor technology and reliability to enhance flight safety. The angle of attack sensor, or AOA sensor, plays a critical role in preventing a dangerous aerodynamic stall. A stall occurs when the angle of attack becomes too steep, causing the airflow over the wings to separate, resulting in a sudden loss of lift. The AOA sensor on the superplane was designed to detect when the angle of attack was approaching a critical level and send a signal to the flight control system. This system would then automatically adjust the plane's elevator to lower the nose and reduce the angle of attack, preventing a stall. However, in this particular instance, the AOA sensor malfunctioned. It began sending erroneous data to the flight control system, indicating that the angle of attack was dangerously high, even though this was not the case. The pilots, unaware of the faulty sensor readings, were suddenly confronted with a series of warnings and alarms, indicating an imminent stall. Section 4. The domino effect, from sensor failure to system malfunction. The flight control system, responding to the faulty data from the angle of attack sensor, initiated a series of automated actions designed to prevent a stall. This sensor, which measures the angle between the wing and the oncoming air, is crucial for maintaining safe flight. When it malfunctions, the consequences can be dire. The system, interpreting the erroneous data as a high angle of attack, believed the aircraft was at risk of stalling. The system automatically pushed the nose of the plane down, attempting to reduce the perceived high angle of attack. This action is a standard safety measure designed to prevent the aircraft from stalling by increasing its speed and airflow over the wings. However, in this case, the plane was not actually in a stall condition. Because the plane was not actually in a stall condition, this action had the opposite effect. The pilots, unaware of the sensor malfunction, were confused by the sudden and unexpected behavior of the aircraft. They had no reason to suspect that the angle of attack sensor was providing faulty data. By pushing the nose down, the flight control system inadvertently caused the angle of attack to increase further, pushing the plane closer to an actual stall. The pilots, now struggling to regain control, were faced with a rapidly deteriorating situation. The more they tried to correct the plane's descent, the more the automated system counteracted their efforts. The pilots, struggling to understand why the plane was behaving erratically, fought against the automated system. Alarms and warnings began to activate, adding to the confusion and stress in the cockpit. The situation was becoming increasingly dire as the pilots wrestled with the controls, trying to override the system's actions. They attempted to pull the nose up, but the flight control system, still receiving faulty data from the angle of attack sensor, continued to push the nose down. This created a dangerous feedback loop, where the pilot's inputs were directly opposed by the automated system. Each attempt to correct the plane's attitude was met with resistance from the flight control system. This created a dangerous situation where the pilots were essentially battling against the plane's own control systems, a conflict known as a mode confusion. Mode confusion occurs when pilots and automated systems are not in sync, leading to conflicting actions. In this case, the faulty sensor data had set off a chain reaction, turning a manageable situation into a potential disaster. The struggle between human and machine highlighted the critical importance of reliable sensor data and the need for pilots to have clear, unambiguous control over their aircraft. Section 5. The descent. A chain reaction becomes unstoppable. As the pilots fought to regain control of the aircraft, the situation escalated rapidly. The plane, caught in a tug-of-war between the pilots and the malfunctioning flight control system, began to lose altitude rapidly. The pilots, now facing a critical emergency, desperately tried to understand the root cause of the problem. However, the cascade of alarms and warnings, coupled with the plane's erratic behavior, made it incredibly difficult to diagnose the issue quickly. The faulty angle of attack sensor had triggered a chain reaction, leading to system malfunctions, pilot confusion, and ultimately, a loss of control. The once reliable systems designed to protect the aircraft and its occupants had tragically become a contributing factor in its demise. The situation highlights the crucial importance of robust sensor technology, accurate data interpretation, and the need for clear communication between automated systems and human pilots, especially during critical flight phases.